This is the TRS-80 Deluxe Joystick. This joystick was introduced originally for the Radio Shack Color Computer, but later was introduced in a 2-button version for both the Color Computer and the Tandy 1000. So in the 2-button version, you've got a second button there. If you're not a TRS-80 fan, you might still recognize this joystick from a couple of other machines. It was the standard joystick on the IBM PCjr, and they were sold for the Apple II as well. Now, these joysticks were not made by Radio Shack. They were made by a company called Kraft, and that was a popular brand of joysticks back in the day. The Deluxe joystick's pretty rugged. It's got, nice plastic to it, high quality plastic. This is a potentiometer style joystick, so it has variable motion between each point. In the 80s for sure, we considered this to be a superior joystick type to say what the Ataris used, which were just 8 switches or 9 switches or whatever that allow you to go up and diagonally, etc., etc. This allows you to vary your motion, and we always thought of that as a bonus for sure. And it made it possible to use this controller to operate things like a drawing program or flight sim. It was nice with, so that was good. This joystick also has a couple of tabs on the back that let you set it to a free-floating or a spring return motion. So you can get rid of that spring return to center action if you don't want it. So exciting news, I have a new screwdriver. This is to celebrate 1,000 subscribers on my channel. And I want to take a second to thank each and every one of you for clicking that subscribe button. That's really the inspiration that makes me want to make more videos. And I really appreciate the fact that, there's 1,000 people out there who want to see some of this stuff that I pull apart. And it's really gives me a great feeling. So thank you very much. And now I can pull things apart safely. So there's 2 screws at the top, there's 2 screws on the bottom of this thing. We'll pull them out. Look at that, this safe screwdriver. It's working perfectly. Nobody needs to worry anymore. And the back just comes off, and you can see those 2 flippers there. Oh, and I just lost a screw. Pretty straightforward. Inside, we've got a couple of potentiometers, which is what we really expected. And they are connected through sort of a complicated gimbal mechanism to the actual joystick. And you can see, as I move this back and forth, you can see it's changing the position of the potentiometer. As long as I get my finger out of the way, you can see that. So you can see that, and then there's my y-axis going back and forth. I'm going to zoom in and we can take a closer look. Okay, so there we are. Now, these guys, they come out, and you can actually remove that whole unit. So I'm going to pull that out, and this is going to kind of explode. Hopefully it doesn't explode too badly. Okay, perfect. Yeah, this is the actual potentiometer unit. And you can see that it's just a spring-loaded mechanism there. You can see that spring there. And as you move the joystick, it stretches that spring out, and that's your return to center. The trim is right here. This is kind of cool because this trim, see what the trim does? It actually moves the potentiometer back and forth. It physically just shifts the position of the pot. That's kind of cool. The pot itself is a 100K pot. I think all variable joysticks, all potentiometer-based joysticks of the era were all 100K. There were different methods of reading the values, but the pots themselves were the same. The little levers that turn off the return to center are actually implemented by stretching out this spring. So there's a hook right here, you might be able to see it, and the lever catches that hook and it stretches that spring out. And see, when the spring is stretched out like that, it's hard to do this. Hard to do this and show you, but you can kind of see, hopefully, that the, try the angle a little different here. You see the potentiometer doesn't return to center when that spring is extended, just free floating. Then flip it back and then it returns to center. The switch, pretty unexciting. It is what appears to be just an off-the-shelf kind of switch you might even buy at Radio Shack. In fact, I would almost swear this switch you could buy at Radio Shack. It's interesting, in the 80s, a lot more stuff was built without custom, moldings. This is an off-the-shelf switch. Nowadays, they would get the switch custom molded for the controller. It would be all, perfect. But yeah, in the 80s, just did what worked. There's a date code on this. It is 5A4. I'm not sure if that's 1985 or 1984. I'm going to guess it's 84. Anyways, it's from the 80s, I know that much. We'll take a look at how this works in the upcoming segments. Color Basic has a function to read the joystick values, and I've used that to create a little program that's just going to read out the joystick and print it on the screen. So let's run that. And you can see it's at 32. If I move the joystick over to this side, 63, which is the maximum value, and on this side it's 0. And then as we go along, it varies back and forth between that 0 and 63. Because it's 0 to 63, that indicates it's a 6-bit A to D converter inside the color computer, and we'll take a look at that in a second. This is the relevant part of the color computer schematic for the joysticks. There's 2 ports. There's joystick 2 up here and joystick 1. The joysticks themselves are just simple voltage dividers, so 5 volts comes in from here and flows into pin 5 on both plugs. Pin 3 is your ground, and pin 1 and 2 are your outputs. Pin 1 is X and pin 2 is Y. Now these, like I said, are simple voltage dividers, so essentially when you plug a joystick in, there are 2 resistors that connect like that. What this means is that if the joystick is in a center position, there's going to be somewhere around 2.5 volts coming out on pin X. That goes into this Joy 0 pin on the SC77526 chip. Now this chip is a custom chip that was created by Motorola for Tandy. I don't think it's used on any other Motorola products or products that Motorola supplied. I think it was only Tandy that used this chip, but it is created by Motorola. So it kind of shows the clout that Tandy had back in the early 80s to actually get Motorola to make a custom chip for them rather than having a smaller firm make it for them. The way this chip works is that you apply a digital value to these 6 pins, so this is your 6-bit input, and if that value is lower than the value here, the CMP or comparator output will be 0. If it's higher, it'll be 1. So for example, let's set these all to 1. So this is a value of 64. Technically 63 because it's 0 based. This value here, if we assume this is 2.5 volts in, is going to be lower than this 64 because the digital value should be about 32 for halfway. What's going to happen is this comparator output is going to be 0. As a second example, we're going to set this to a much lower number. So we'll go 0, 0, 0, 0, 1, 1. So this is 3. This is inputting at 2.5 volts still, which is roughly 32. So this digital value is lower than this value here. The comparator is going to show up as 1. This digital to analog converter chip is actually used for a few functions, not just the joysticks. There's a sound enable input here that, if set, will actually output sound on this line, and it's going to output a sound based on what you input on these digital inputs. The other thing it has is it has a cassette output. So this is just another sound output essentially, but it's right here. When we're checking the joystick values, we actually turn the sound enable off. That way we don't get a bunch of noise when we're hunting for the actual value that the joystick is set to. One thing worth noting is that on the Color Computer 1, the SC77526 chip doesn't exist. It's actually implemented entirely using discrete components. I might do a follow-on video comparing the two circuits because it's interesting to see how a discrete circuit design has been converted into an IC on this, but we'll save that for another time. I'm not going to spend too much time talking about how the joystick buttons work. It's actually quite simple. Pin 4 is connected via this long lead all the way down to the keyboard PIA right here. It's actually connected to the first scan line of keyboard keys. In order to distinguish between a keyboard key being hit and the joystick button, there's actually a connection into a 74LS30, which is an 8-input NAND gate, and that connection goes into the gimme chip. And that allows the computer to tell that it's actually a joystick button being hit and not a keyboard key. On the screen I got the disassembly of the code from the Color Basic Unraveled book. To be honest with you, the comments are not always the clearest, so it took me a little while to go through this and figure it out, and I thought I'd share that with you on this video. I've also got on this side the A and B registers and the values of the PIA 0 and PIA 1, and here I got the stack just on screen so you can see as I step through this code. The initial part of the code is just some setup. There are two loops in this code. There's an inner loop which loops through 8 times, and there's an outer loop which loops a maximum of 10 times. So it's basically 2 loops reading the joystick, getting the value, figuring it out, and then outputting it and storing it in memory. For this example, we'll assume the joystick is set at what would come out in BASIC as 46, so kind of, 2/3 of the way to the right. That value, if you shift it left 2 times, comes out to be 184. So 46 times 2 is 92, 92 times 2 is 184. The code gets interesting here at LA9EB, where we load the A and B registers with the values 40 and 80 hex. So those are loaded into A and B. You can see 40 hex there, which is equivalent to 64 decimal, or 010000 in binary. Likewise, in the B register, we have 80, and that is equivalent to 128 decimal, and that is 1 with a bunch of zeros in binary. The A register is a shift counter, so basically this bit here gets shifted all the way to the right, and when it ends up in this final position, that means the inner loop is done. It is also used as the sort of hunting value, where we add it to the B register value, which is our test value. We add this value or subtract it, and that gives us our new value to test from. And I'll explain that in a second. But you'll notice that 40 or 40 is half of 80. And that's important because it goes through and it does a search looking through half of the set each time. The next thing we do is store the contents of the A register in the stack. So 40 is now in the stack. Then we need to do a little bit of magic. So we need to set this bit here in the B register so that when we copy that into the PIA, the serial port is disabled. If you don't do that, what's going to happen is a bunch of junk is going to come out on the serial port, and if you've got a printer connected, well, you get a bunch of junk on the printer, so we don't want that. So we'll set that in the register, and then we're going to copy the contents of the B register into PIA1. So store B into DA, which is digital to analog converter, which is also AKA, in this case, PIA1. It's stored in PIA1. You can see that 8.2 value is in there. And what happened electrically is that this line PA7 went high, and this line PA1 went high. PA7 is our data going into the digital inputs of the digital to analog converter. PA1 is the disable line for the serial port, which goes into the serial chip. Once we set the digital inputs, the joystick input is going to be compared to this digital value, and there's going to be an output on this compare line. It'll either be low or high depending on how these relate to each other. So in this case, it went high because the value that we put in was 130, or was actually 128, and the number we're looking for is 184. The joystick is sitting at what should be 184. So it is saying the number that you're looking at here is lower than what I'm seeing on the input on the joystick. Now we clear the setting in the B register just to clean up. In the next step, we take the value from the PIA and we put it in the A register. This value can be considered either a signed or an unsigned value. In this case, I'm using it as a signed value, which means all ones, FF, it's going to be negative 128. Now, if I was using this as an unsigned value, it would actually be 255 when I converted it to decimal. But in the computer itself, the representation is the same. It's really how you use the variables, how you use those values that adds a meaning, whether it's signed or unsigned. So anyways, we're going to use it as a signed value. And in the next step, we do a BMI, which is a branch minus. And the A register definitely is minus. It's minus 128. So we're going to go to A9FF because it was minus. So we're at A9FF. And the instruction here is to add to the B register the value of the stack. The stack value is 40. So it's going to add this to the B register. And it did. And that's set to C0 now. So you can see how the value in the B register went from 128 previously to 192 because we added 64 to that value. 64 is half of 128. So what it basically did is it said, I'm too low. Okay, let's search for a higher number. So we're going to search half of what our current search setting is, which was 128. We're going to search half higher. So it's going to split the range of possible values in half. And it's going to ask again, is it lower or is it higher? So this is a way to quickly search through the range of possible values without having to say go through, value 0 to 255 and search for every single one, having to do 255 comparisons or 256 comparisons. This way we can do it in, I think, 8 comparisons, and it will give us the result. If you know your algorithms, this might look a lot like a binary search. It is pretty close to a binary search, but it's not a pure binary search, and that threw me initially when I was looking at it. It certainly takes some of the concepts, but it's not 100% an implementation of a binary search. Okay, so we've added that number, and then the next thing we're going to do is we're going to take the stack value and we're going to load it into A, and we're going to pop it off the stack. So there we go, it's in A. And then what we do is we shift this to the right. And the reason we do that is because this value, this 40, that, as I said, it's a shift counter. And when the bit gets over all the way to the right-hand side, that means our inner loop is done. So we shift it. The value is now 20. It's not only the shift counter, but it's also that modifier value that we add or subtract to our hunt value that we're looking at. And we compare that now to 1. That basically will tell us, if the A register is 1, our loop is done. It's not done, so it's going to branch not equal back to the top of the loop. So we're back at A9EE. And we continue the process, except this time the initial values aren't 4-0 and 8-0, they're 2-0 and C0. Okay, so we copy A into the stack, we set that flag so the serial output is off, and then we store the B register in the PIA to get our value, and then we clean up, and then we load the value from the PIA 0 into the A register, and you can see that the value there is 7F, or 127. The important bit is this one right here. That's our comparator bit. And the reason it's 127 is because 192 here, when compared with 184, is actually higher. So it's saying the number's too high, you've got to go lower. So we do exactly that. We subtract from the B register the value that's in the stack, and that's 20. We subtract that, and now we're at A0. So our search value is 160. Now this is lower than 184, so the next time we do a test, it's actually going to come back with a 1 saying your number's too low. This statement here is a fancy way to skip over a bit of code. The reason we do that is because this is the add routine, so we just skip it. Like we did in the last iteration, we pull the modifier value off of the stack and load it into A, so 2 zeros in there. And then we shift it right once, which changes the 20 to 10, it divides it in half, or 16 decimal, and you can see the bit moved over 1 space to the right. We compare the value in A with 1. Now if the bit was all the way to the right, it would be 1. It isn't. The next line is branch not equal to A9EE, and that will happen because it is not equal to 1. We trace through the code for 2 iterations, but let's take a look at how the algorithm works through a whole set of iterations to come up with the answer. So the first thing, it always starts halfway through the 8-bit data space, which is 128. And when we compared with 128, the value was lower than 184, so the result from the comparator was 1. We add 64, or half of 128, and that gives us 192, and we compare that with 184. Well, this is higher, so the comparator returns a 0. In the next step, we take 32, and we subtract that from 192, because the value is too high. And we can see here that the comparator came back and saying the value is now too low. So 160 is less than 184. It's too low. Okay, so we're going to add 16, which is half of 32. Now our value is 176. It's still too low. So we're going to add 8, and we get to 184, which is the value we're looking for. And this is why it's not a pure binary search, because there's no way for the comparator to say you've got the right value. It can only tell you it's lower or higher. So what it does is if you get the correct value, it's going to say it's lower, meaning you've got to test again with a higher number to see if that is higher than your target. If it was a pure binary search, within 5 iterations it would be done. I think 4.2 iterations on average it would be completed. It isn't, so it's going to keep doing a couple more loops looking for the correct value. Okay, so the comparator said the value's lower, so we're going to add 4, which is half of 8, to the current target value. So now it's 188, and of course the result comes back lower. Okay, you got to look lower. So we're going to go and subtract 2 from that value, so we're at 186. Got to go lower still. Half of 2 is 1, so we're looking at 185. Got to go lower still. Okay, 185 is really close to 184. It's, with the fact there is only 6 bits of resolution versus 8 bits, it should be fine. It'll work out in the wash. So how does that all work? Well, it's a little bit of a trick. We shift the value that we came up with as 185 over 2 bits to reduce it down to 6 bits, because the digital to analog converter is only 6 bits wide. And magic, the answer is 46. So that shows you how the algorithm hunts for the value that the joystick is set to. I'm not 100% sure this is the best way to do it. It's possible the commercial realities, needing to get the product out the door, meant that the implementation isn't ideal. But it looks pretty good to me. If you've done a lot of work with search algorithms like this, or you know more assembly language than me, which is pretty easy, put a critique in the comments below. I'd love to hear what you think about this algorithm. This chart here shows how the algorithm arrives at certain values. So these values here are the joystick values, 31, 71, 185, 251. And you can see it starts at 128, and it'll either add 64 or subtract 64. And then it'll either add 32 or subtract 32. And then it'll either subtract 16 or, well, in this case, subtract 16 again. Here we got adding 16. And it just keeps going along. And as it goes through each iteration, it gets closer and closer to the final value. The last thing I want to do is just take a quick look at how this works electrically. To do that, I've set up a bit of a test rig here. I've got a Coco 3, I've got an oscilloscope, joystick, and of course a monitor. And the joystick is currently centered. And you can see it's right about 1 volt. So this is different than what I said earlier in the video when I was looking at the code and the disassembly. Disassembly said I should get 2.5 volts there, which isn't entirely accurate. So it's actually closer to, well, it is 1 volt essentially. If I move the joystick back and forth without the program running, the voltages don't change at all. They stay at 1 volt on that input. I'm going to run the program, and you can see that now the voltages are changing as I move the joystick back and forth. And there's a little bit of noise here that's coming across. I'm going to apologize first off. This oscilloscope has got a sort of bad display. I think the power supply needs some work. Unfortunately, my favorite oscilloscope was dead when I tried to use it, and my logic analyzer, which I also wanted to pull out, it was dead as well while I was recording this. So I got a lot of test equipment repairs I need to do in the near future. Anyways, let's try to get this signal to look nice here. Stop scrolling across. Should be able to. There we go. There's a bit of a glitch here, and that appears to be something in the digital to analog converter when it's being activated. There's some code obviously doing some work at this point, and that's causing the voltage to drop to about 0.5 volt. When I move the joystick all the way to the left, it goes down to the 0.5 volt setting. So I'm going to just put my measurement right there. You can see it's a 0.52 volts. And then I'm going to move it all the way up, and it goes to 1 volt. So I'll just measure that just for fun here. Oh, it goes to 1.5 volts, sorry. 1.55, 1.56, no, let's say 1.5 volts on there when it's all the way to the right. So back and forth, it's going between 0.5 volt, centered is about 1 volt, 1.5 volts to the right. I've gone ahead and connected the scope to the comparator out of the D to A converter. This isn't the ultimate tool for the job, but it'll give us an idea of what's happening on the comparator output. Right now the joystick's centered, and you can see that there's a pulsed output coming out of that comparator. That's because the D to A converter is being asked to look for a lower value, higher value, etc., etc. And it's something like 50-50 between being off and on. If I move the joystick all the way to the left, our value goes to 0, and a much larger percentage of those comparator output comparisons are going to be 1s. And that's why this line is much more solid than it was when the joystick was centered. When I move the joystick to the right, you can see there's a lot less data here, so there's a lot less 1s coming out. And the reason is because it's right at the top, and that comparator is going to return 0 for the vast majority of queries that go into it. Well, I'd like to thank you for watching my video. I really hope you enjoy this kind of content. If you like what I'm doing and you're not subscribed yet, please subscribe. If you are a subscriber, thank you so much for subscribing to my channel and listening to me. I really appreciate it, and I'm so happy for each one of you who has decided to subscribe to my channel. Thanks again for watching, and I'll catch you next time. The joystick has some nice trim tabs on it, so you can center it. And if we flip it over, it has a couple of switches on the back, or levers, that allow you to change it so that it doesn't spring return. So I flip that over, and then, well, that didn't quite work. I'll flip it over again. Oh, it's gonna work. There we go. No. This problem actually, I remember way back when, always having this issue with it. Okay, so maybe this will go in the blooper reel. Who knows? Let's try the vertical. Let's see if that works better. Okay, spring loaded, and come on, there we go. No. This joystick also has a couple of tabs on the back that let you set it to a free floating or a spring return motion. So you can get rid of that spring return to center action if you don't want it.